Hello, welcome to this lecture video on the topic algebraic properties of matrix operations. So I'm teacher Melai. So first, we are going to consider the following definition. So like for instance, the definition of equality. So if we let A and B be matrices, then A is equal to B if and only if A and B have the same dimension, and A sub ij is equal to B sub ij for all I and j. So we can say that A and B are equal if and only if it satisfies this condition. So which means if we are going to consider, for instance, matrix with the following values. So let's say 1, 2, 3, 4, 5, 6, 7, 8, and 9. And another, so let's have 4, 5, 6, 7, 8, 9, 10, 11, and 12. And let's consider another one. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this following matrices, so we can see that the number of, or we have the same orders for A, B, and C, and that is 3 by 3. So they have the same order. So it satisfies the condition number 1 that that the matrices have the same order, except that if we are going to inspect the elements, so as we can see here, the elements in the B are not the same with A and also not the same with C. But our A sub ij, or the elements rather of A, set A is equal to the elements of C sub ij, which means that A and B are not equal, but A and C are equal. Okay, so let us move to the next slide. So let's go back to our slide. Okay, number 2. So second definition, so the sums and differences. So in our discussion of the sum and differences, we were able to discuss or to show that the sum of, or the sum and differences of two matrices or more can be performed if and only if they have again the same order or the same dimensions. And just like how it is defined here, so if we let A and B be matrices, if A and B have the same dimensions, then the sum A plus B and the difference A minus B are defined, and their entries are given by. So we have A plus B, parenthesis A plus B, sub I sub j is equal to A sub ij plus B sub ij. And for our difference or subtraction, the parenthesis A minus B I sub j, so the entries here, so it is equal to A sub ij minus B sub ij for all ij. Okay, next. So let's have also the definitions for zero matrix. So the M times N zero matrix 0 is the M times N matrix whose I sub j entry is given by. So it is 0 sub I sub j is equal to 0 for all ij. So we have what we call as zero matrix. So if all the entries are 0. Okay, so let us consider now the different properties of matrix operation. So for our theorem 1.1, it states that if we let A, B, and C be M times N matrices, then the following properties hold. So we have A plus B is equal to B plus A. So we are familiar with this property. This is the commutative property, or since we are very particular that this A and B represent matrices, so it is a commutativity of matrix addition. While in our second one, if we consider another matrix, matrix C, so if we're going to group B and C, so in our left side, and then we are going to group A and B on the right side. So we have here A plus the parenthesis B plus C is equal to the parenthesis A plus B plus C. So you are going to get the same answer whichever you compute first. So if you compute, for instance, the sum of B and C first before adding it to A, or if you computed for A and B first before coming up with letter C. Okay. And then for letter C, there is a unique matrix 0 such that A plus 0 is equal to A for any M times N matrix A. So the matrix 0 is called the zero matrix, and it serves as the additive identity for the set of M times N matrices. So we know very well that in additive identity, the result must be itself. So the number that you're going to add to get the same matrix is zero matrix. So zero matrix serve as additive identity. Okay, so for letter D, for each M by N matrix A, there is a unique M times N matrix D such that A plus D is equal to 0. So we usually denote D as -1. So we have A plus a negative A is equal to 0. So we call negative A and the additive inverse of the matrix A. So we note that, of course, negative A is equal to the negative 1 multiplied by A. Okay, so we still have here other definitions to be considered. So if, for instance, for definitions of multiplication, so if we let A be an M times N matrix, let B be an N times P matrix, the product AB is M times P matrix whose I sub j entry is given. So if you will just inspect the value here, if you notice, the summation from K is equal to 1 to N, and it's entry A sub IK and B sub KJ. So if you notice, we have the same K here, which is removed, and what is left if it is combined is IJ. So that's for all IJ. So we actually cancel the value of A based on the definition. So it was removed. So the product of A, B, I, J can be defined as summation of A sub IK, B sub KJ, where K is from 1 until to N for all I and J. So similar to what is presented here. Oh, okay. So before we are going to move to the properties of multiplication, let us just consider one proof for our properties of addition. So let us consider the first one. A plus B is equal to B plus A. Okay, so let us clear this first. So if we let A, for example, what we are trying to prove is A plus B is equal to B plus A. So if we let A, B be elements of a real number, or maybe we can just present this first individually. So if we let, for example, A be elements of a real number, and we know that this is in the form or matrix M times N. As I mentioned before, it can also be denoted as M times N, where it means that R is real numbers. So the elements of our matrix A are real numbers. And then we also let B be equal to the elements of real number. So raised to M times N. Now, if we add A plus B, we know, of course, that this is M times N and B is also M times N. And since A consists of elements of real numbers and B also consists of elements of real numbers, then the sum of this is elements of real numbers raised to M times N. And so with, if we are going to interchange this, B plus A, where B is also M times N, and A contains M times N. So this will also result to elements of real numbers raised to M times N. Okay, so in this first few proofs, we were able to show that the result of A plus B and B plus A will be in a form M times N. So this is, of course, an assumption that because we can only add same dimension. So M times N and M times N, representing that they have the same dimension. So the result is M times real numbers raised to M times N. Now, how can we also show that the property holds in all entries, or the corresponding entries in A when added to the corresponding entries in B will also result to the corresponding entries in B added to the corresponding entries in A. Okay, so to show that, we are going to use the definition. So in our definition, we have A plus B. So this is about the entries, the sum and difference. So I, J. And this is equal to A sub I, J plus B sub I, J. Okay, we know that when this will be, since the result is real numbers, we know that the result for A sub ij and the result for B sub ij will be real numbers because it's elements of real numbers. So using the property now of commutativity in the real numbers, so we can actually say that this is also equal to B sub ij plus A sub ij. Using again the definition, so we can actually go back to B sub B plus A sub ij. Therefore, with this proof, so we were able to show that A plus B is equal to B plus A. So that is our proof number 1. So in the exercises that you will be asked to do, you will also be asked to show the proof of other properties. Okay, so let us again go back to our screen or our slides. So for the properties of matrix operations in multiplication, so we have the following. So let's consider this as theorem 1.2. So if we let A, B, and C be matrices of appropriate sizes, then the following properties hold. So we know that we can only multiply two matrices if the number of rows is the same with the number of columns in another matrix, or vice versa. So here we have the associative matrix. So if we multiply, of course, we are referring to the dot matrix here. If we multiply B and C first before multiplying A, this is equal to multiplying A and B first before C. And then for letter B, we also have the right distributive property, that is adding A plus B, then multiplying it to C. Or if you're going to multiply A, C, and add it to the product also of B, C. And the same if we are going to transfer our C to the left side. So it's called the left distributive property. So C multiplied by the sum of A plus B is equal to, when we are going to also add the product of CA and the product of CB. So as you see here, we are of course familiar with what is distributive property means. So we just distribute the value of, or rather the matrix C. C will be multiplied to our matrix A, and C will be multiplied to our matrix B. The same with our C, except that our C, matrix C, is located at the left side. So that's why it is called left distributive property. Okay, so we have the following definitions for multiplication by numbers. So if A is a matrix and K is a number, then KA is the matrix having the same dimensions as A, and whose interest or given by. So we have matrix A, I sub J is equal to K dot A sub I J. So this is for a scalar multiplication. So another definition. So if A is a matrix, then negative A is the matrix having the same dimensions as A and whose interests are given by. So we have the negative A of IJ is of course the same with the negative A sub IJ. Okay, so here are the properties of scalar multiplication. So let's consider this as theorem 1.3. So if we let R as be real numbers and A and B matrices of appropriate sizes, then the following properties hold. So the value of R and C are real numbers here. So R multiplied to S matrix A is the same with or equal with RS, the product of RS multiplied to our matrix A. So we also have here getting the sum of our two scalar values multiplied by matrix A. And if we distribute this, or if we multiply matrix A to scalar R and adding it to the product also of A and scalar S, you will get the same answer. So for letter C, if we are going to involve two matrices and then distribute now the scalar R, so it is R A plus R B. And also with letter D, if we will also consider matrix A multiplied by the product of the scalar value with our matrix B. So it is the same even if we will get first the product of AB before multiplying it to the scalar, or if we get first the product of the scalar and matrix A multiplied by matrix B. So we also have here the properties of the transpose. So let's consider this as theorem 1.4. So if we let R be a real number and A and B matrices of appropriate sizes, then the following properties hold. So if we transpose the A sub t or the transposed A, then you will get, of course, you will just bring it back to its original value or original matrix. And matrix can also be distributed. So we have A raised to t or the transpose A plus the transpose B. You will get the same value if you will the same matrix rather, if you will add the two matrix first before transposing it. Okay, for C, it is also distributive for that product. So A, B raised to T is equal to B raised to T, A raised to T. Or even if we will consider a scalar value for letter D. Okay, so your task will be to show the proofs of all the properties. Thank you for watching.